Okay, section 4.2 is going to talk about the second derivatives. The first derivative told us where the graph function increased and decreased. The second derivative is going to tell us its concavity. Concavity is its curving upward or curving downward. As we can see in this graph, this is curving upward. If I would draw a line segment, if the graph lies below that chord, then it concaves upward. If it lies above, then it concaves downward. When it concaves upward, the first derivative is increasing. When it concaves downward, the first derivative is decreasing. So the first thing we're going to do is find the second derivative. So to find the second derivative, you need to find the first derivative. So the first derivative would be 3x squared. The second derivative is just taking the derivative of the first derivative. Okay, so looking at this example, taking the cube root of x, the first derivative then the second derivative is taking the derivative of that. So we take and multiply. And then again, we have to subtract. So what's happening to our graph with the different derivatives? If the first derivative is increasing, the second derivative will be positive. And it will concave upward, as seen by the examples there. If the first derivative is decreasing, it's a negative second derivative. It will concave downward. So we're going to determine the intervals in which the graph of the function is concaved up and concave down. So in order to do that, we need to take the first derivative and then take the second derivative. So looking at a sign chart, when our x is 0, it's positive. And when it's negative, it's positive. First derivative when it's negative, still be positive. So this is increasing from negative to infinity, and it's concave upward from negative infinity to infinity. Looking at what that graph would look like. It would look like so. It's concave upward for all x, and it's increasing for all x. Let's look at the next one. The first thing we have to do is the first derivative. Then the second derivative. Remember that the natural log of x must be greater than 0. So graphing that, what will that look like? So when the first derivative is positive, or when x is positive, the first derivative is positive. Second derivative, when x is positive, second derivative is negative. So this is going to concave down and increase. Remember that x has to be greater than 0, so what will that look like? It looks something like that. X to the third, first derivative, second derivative. We'll just use 0 as our focal point. So in the first derivative, x is greater than 0, it's positive. When it's less than 0, it's positive. So it's increasing. Second derivative, when it's greater than 0, it's positive. But when it's less than 0, it's negative. So at this point, it's going to change. So from negative, sorry about that. So from negative infinity to 0, it concaves down. And from 0 to infinity, concaves up. So what will that look like? Something like that. So you go ahead and do the matched problems. So if you took notice, especially on that last graph, you saw where there was this point where it changed from concave up to concave down. Or in the previous example, we saw where it went from up to down and down to up. So that point is called an inflection point, where it changes from up to down or down to up. So we have a procedure that we can test for the inflection point. So again, you're going to find your second derivative, find the partition numbers, construct a sign chart like I was doing up above, and then see where the sign changes. If it changes, that is an inflection point. If it does not, then there's no inflection that occurs there. So let's try this example, finding the inflection point. So the first thing we need to do is find the first derivative. And then find the second derivative. So we are going to set that equal to 0. And then we're going to test, just like we did with first derivatives, test that value. With a sign chart. So if I put something less than -1/2 in there, say -1, we'll get a negative number. I put something greater than that, a positive number. So it is down from -infinity to -0.5, and it's up from -0.5 to infinity. So find the inflection points for this example. You should have found that the point was 3, and if you substitute that back into the original function,